Hello. As we've seen, truth tables provide us with an infallible method for determining whether an argument is valid, or whether two sentences are equivalent, or whether a given sentence is a logical truth. However, in a way they are a bit inefficient. For one thing, as you add more atomic letters to the sentences you are testing, truth tables start to get unmanageably large very soon. Imagine that you're making a truth table for this sentence. Remember that the number of rows needed in a truth table is 2 to the power of n, where n is the number of atomic sentences, also known as sentence letters. In this case, we have 2 atomic sentences, so the number of rows is 4. But what happens if we add another sentence letter, as in sentence 2? Now the number of rows gets up to 8. And if we add another letter, we double the number of rows again. Notice that this is not a particularly long or complex sentence. And at 5 sentence letters, the table looks positively wild. And you can see that tables get big fast. The graph on the right shows the number of rows against the number of letters, and it displays what is called an exponential growth pattern. Part of the problem is that a table tells you how things turn out for the sentence in every possible case. So it explicitly gives you 2 kinds of information. It tells you in which cases the sentence is true and in which cases it is false. Now, clearly, one half of this information is redundant. Given that in SL every sentence must be either true or false, and given that in a given assignment a sentence is false if and only if it is not true, we don't need to be told in which cases a sentence is true and in which cases it is false. If we're simply told in which rows a sentence is true, we immediately know in which rows it is false, right? It is in all the other rows. The truth table approach is as if, after telling you that in the Super Bowl matchup between the Eagles and the Chiefs won, I then proceed to tell you, oh, by the way, the Eagles lost. The last commentary was completely unnecessary, unless I was talking to a particularly obnoxious Eagles fan. Okay, having exhausted my knowledge of American football, I will now introduce a leaner, more effective alternative to truth tables. This alternative is called the truth tree method. Instead of telling you where sentences are true and where they're false, truth trees get down to business straight away and zero in on the cases in which a sentence is true. As a matter of fact, you don't have to limit yourself to a single sentence. You can start with a set of sentences, and a truth tree will list those cases in which all the sentences in the set are true, and only those. So, what is a truth tree? A truth tree is a device for displaying all the truth value assignments, cases, examples, models on which all of the sentences in a given set come out true. A truth tree breaks down complex sentences into simpler ones, specifically those sentences that must be true for the original sentence to be true. Take sentence 1, for instance. For it to be true, both 2 and 3 must be true. And since we already broke up A and B or C into its immediate components, we add a checkmark next to it to indicate that we need not consider it any further. A does not need to be checked because it cannot be broken down into smaller sentences. Now let's proceed to the only remaining compound sentence, which is number 3. For B or C to be true, either B or C must be true. But these are 2 different possibilities, so we must branch out to consider each case separately. In analyzing a disjunction, we must branch out because there are 2 ways to make it true. In contrast, when breaking out a conjunction, such as our topmost sentence, we have to stack formulas. This is because there is only one way to make a conjunction true, namely by making both of its conjuncts true. Thus, there is no bifurcation into alternative truth-making assignments. Also, notice that our tree has 2 branches, which, abruptly changing metaphor, we'll call paths. Each path corresponds to a kind of assignment in which the original sentence, A and B or C, comes out true. The left path corresponds to those assignments in which A is true and B is true. In a truth table, this would correspond to the first 2 rows. Notice that in this path, the value of C is irrelevant, because if you make both A and B true, the sentence will come out true no matter what value C takes. The other path corresponds to those assignments in which A is true and C is true. This would match rows 1 and 3 of a truth table. As you can see, now it is the value of B that is irrelevant. Here's another example. Let's do a truth tree for this set of sentences. Let's start by checking the topmost sentence, which is a conjunction. The only way for it to be true is for its two conjuncts to be true. So we check it and list them below. Now we deal with the only complex sentence we have left, which is the disjunction C or B. There are two ways in which this sentence can be true, depending on which disjunct we choose. So we add a check mark and we open two branches, one for each disjunct. However, notice that the right side branch contains a contradiction. It is B and not B. This means that this path doesn't contain a viable assignment, because no possible assignment can assign both true and false to a sentence. In consequence, we add an X at the bottom of the path, that is to indicate that the path is closed, since it contains a contradiction. So there is only one assignment in which both A and not B and C or B come out true. It is the left one, in which A is true, not B is true, but since we know that whenever not B is true, B is false, B must be false in this assignment. Finally, C gets to be true. Again, and this is the last time I'll show you a truth table, this assignment corresponds to the third row of the joint table for the two sentences in the set. You can see that this is the only row in which both A and not B and C or B come out true. In all the other assignments, at least one of them comes out false. Yet another example. Let's make a tree for this set of sentences. First, let's list them. Where should we start breaking up our sentences? A good rule to follow is to start with those sentences that yield stacks, rather than branches. So whenever we have a conjunction and a disjunction, we should start with the conjunction. In this way, we'll end up with a smaller and more user-friendly tree. So we may start with either C and B or D and A. It doesn't matter. Let's start with C and B, since it's the one at the top. So we check it and do our stack of sentences. Next, we do D and A. And this is what we get. Everything is straightforward so far. Now, the only compound sentence left is, if A, then not B or not C. How are we going to break it up? Remember that there are two ways of guaranteeing the truth of a conditional. One is by making the antecedent false. The other is by making the consequent true. Thus, as I'm sure you'll remember, a conditional is equivalent to a disjunction in which the left disjunct is negated. So we're going to treat if A then not B or not C as equivalent to not A or not B or not C. So after checking off the sentence at the top, there are two ways for not A or not B or not C to be true. One corresponds to the left disjunct, not A. The other one to the right disjunct, not B or not C. We're not done yet, since we still have one unchecked compound sentence at the bottom, namely not B or not C. So we add the check mark and do the customary branching. Now we're done breaking up our sentences and our tree is done. Question: under which of the paths do all the sentences in the original set come out true? Well, we ended up with three paths. Let's check each in turn. The leftmost path contains both A and not A. This is not a viable assignment. So we close it off with an X. The center path has B and not B, so we close it off too. And the same goes for the rightmost path, but now with C and not C. In sum, all of the branches contain contradictions. Thus, the tree shows that there is no assignment in which all of the sentences in the set come out true. I hope this has given you a clear idea of what truth trees are about. Now we need to get formal and provide some definitions so we can be completely clear about the terminology we'll be using. A path of a tree is a complete column of sentences from top to bottom. A path is closed if and only if it contains both a sentence X and its negation, not X. Otherwise, the path is open. Remember that an open path corresponds to an assignment or group of assignments of truth values to the sentence letters occurring in the set. A tree is complete when every path is closed, or every sentence that is neither atomic nor the negation of an atomic sentence is checked off. That is, once you reach a point in which you can no longer break sentences into smaller ones, you are done. Your tree is complete. Now it's time to join up the topic of trees with one of the other subjects we discussed earlier. I'm talking about logical consistency, a property of sets of sentences. Remember that a set of sentences is consistent just in case it is possible for all the sentences in the set to be true at the same time. We clarified that further by saying that what is meant for all possible sentences to be true at the same time is for there to be at least one assignment in which all the members of the set turn out to be true. Now we can define consistency in the language of truth trees. A set of sentences is consistent if and only if the joint tree T corresponding to the set is complete and T has at least one open path. So one of our previous examples was this set of two sentences. The tree we did was complete, since at the end, none of the unchecked sentences could be broken down any further. And furthermore, one of the paths remained open. Thus, the initial set is consistent. Also, we can read off the path the assignment or assignments that make all the members in the set true. The procedure for doing so is the following. If a letter shows up in the path, the assignment sets that letter to T. In this path, we have two sentence letters, A and C, so the assignment sets those letters to T. Also, if a letter shows up negated, then the assignment evaluates that letter to F. So our path contains not B, and in consequence, our assignment gives it an F. Finally, if a letter appears in the set but is not in the path, then its value is irrelevant. The set will be true regardless of what value we give to that letter. So in this complete tree, the left path indicates that making A and B true is enough to make the sentence true. By the way, here we have a set comprised of only one sentence. The value of C doesn't make a difference, so we are implicitly given two possible assignments, one with C true and another one with C set to false. Same with path 2, which includes A and C but says nothing about B. This one implicitly contains two assignments, one in which B is evaluated to true and one in which it is evaluated to false. Okay, back to our definitions. The last one is this. A set of sentences is inconsistent if and only if the joint tree corresponding to the set is complete and all of the paths in T are closed. Earlier on, we saw that the tree for the set of sentences to the left had all of its paths closed. This means that no assignment can make all the members of the set true, and so that it is impossible for all the sentences in the set to be true at the same time. Hence, by definition, the set is inconsistent. Okay, this is all for today. Bye.